YouTube. In this video I'm going to go through a very informal explanation of what we call the binomial theorem. Okay, so the binomial theorem says what it means what it says. It involves binomials, but let's go ahead and start with the whole idea behind the binomial theorem in the first place. You'll notice that I say consider the following powers of binomial expressions. What I want to do is expand these and simplify them. Okay, so you notice that we have a plus b to the 0 to the first to the second to the third. In general, what we're going to be doing in this video is we're going to go ahead and multiply these out if necessary, but what I want to do is look for patterns that would allow us to generalize what happens in general when you have some binomial, some a plus b expression to the nth power, because what we're going to notice here is this. Well, I guess we can go ahead and do a few of these. We say a plus b to the 0, that's not going to be any problem. Of course, we get a plus b to the 0 or anything to the 0, except for 0 to the 0 is 1. And anything to the first power is, of course, going to equal itself. So when we do a plus b to the first power, we get just a plus b, and I'll put a box around that. But I hope you can see this. When we talk about a plus b squared and a plus b to the third, the unfortunate thing for us is that we're actually going to have to multiply these out, which involves distribution. Okay, and so a plus b squared, that's, we learned FOIL in algebra, but if you can imagine already, man, if I have to do a plus b to the third or anything higher than this, what it's going to spell for us is essentially this. We're going to have to go ahead and FOIL the first two factors out and get a product there, some product that we can put in this quantity here, and then we're going to have to go over here and say, now let's take that times the a plus b, and imagine this. What if we had a plus b to the fourth? Well, we'd have to do this orange quantity here times this binomial, get an answer there, and then take it times another a plus b, where each time you're really building on the complexity of what it is that you're multiplying. So it is to our benefit to say, well, let's go ahead and do a few of these and see if we can pick up on a pattern, because if I can, then really maybe we can generalize what would a plus b to the nth power be and not have to actually go through all of the foiling process or distribution processes that come with all of these. So let's go ahead and at least take a look at a plus b squared and a plus b to the third and see if we can deduce a pattern here or infer a pattern. But as far as a plus b goes, this is just FOIL. So we're going to say a times a times b times a, b times b. But a times a, it looks like we get a squared. A times b is ab, so plus ab. B times a, well, that's a times b is same thing. And we say b times b, this is going to give us b squared. And of course, combining like terms, we have a 1ab and a 1ab here. So if we were to combine these out, we say our final expression would look like this. We say a squared plus 2ab plus b squared. So this is our a plus b squared product here. So a plus b to the 0 is 1, a plus b to the first is a plus b, and then a plus b squared is a squared plus 2ab plus b squared. Now, what I know about a plus b to the third is at least this, it'll save us a little bit of time, but we already did a plus b times a plus b, these two things here, and had gotten this product. So I'm going to go ahead and I'm going to substitute this in because I know that's what I get, a squared plus 2ab plus b squared, and then what we're going to do is we're actually going to distribute this. We're going to multiply this out. So we say a squared times a, we're going to get a cubed. A squared times b, we just get a squared b. So we're done with our a squared here. Let's go ahead and take a look at our 2ab. If we were to take 2ab times a, we would get 2a squared b. And if we take 2ab times b, we would get 2ab squared. So plus 2ab squared. So we're done with our 2ab, our middle term in this trinomial. And we say now b squared times a, this right here, we would get plus a single a and two b's, ab squared. And then b squared times b, we'd get b cubed. So the only thing we need to do here is combine some like terms. And notice that this has an a squared b, this has an a squared b. We say, how many total a squareds b do we have here? And so we say, okay, well, we got this a cubed in front, a cubed, plus 1a squared b, 2a squared b. This is going to be 3 total of these a squared b things. So done with those, and we say 2ab squared and 1ab squared gives us 3 total 1ab squared, so ab squareds. And then we say, okay, so plus b cubed. All right, so one thing I want to do is this. I'm going to put a box around this. Is I want to start to look for patterns here, at least in what we see. So when we took a plus b to the 0, of course we get 1. But when I took a plus b to the first, you notice I get a to the first, b to the first. When we take a plus b to the second power, we get now a in front. We've started with a before in here in the front, but we get a squared. I'm going to ignore this coefficient in the middle, but over here we get a to the first, b to the first, and then the very last term is b squared, okay? So when I took this to the second power, you notice that a is starting in the front with all of this second power right here. And as we go to the right, A is now to the first, but now B is to the first power. B gained a power where A lost one of that power. And what I mean by this is A had squared on it first, now A has a first power, but B is now growing in size. We say B the first. Until we get over here, we say now I have no A's left over here, and B is carrying all of this second power weight. And this is actually, essentially the pattern here. We say on the, this one here where we took it to the third, we say A is in the front, but you notice A is starting with all of that third power. But as we go to the right, look what's happening to the powers on A and B. We say A is now going to be taken to the second power. It lost one of this 3, and B gained 1. So we say A squared, B to the first. As I go one more to the right, now A is not going to be squared, it's going to be to the first power, and B is going to be one more, it's going to be B to the second power. And then as I go one more to the right, A is going to lose another power, and if I said A to the first, take away another power off of that, it'd just be A to the 0. So that A is gone, we have no A's, and B has all the power here. So really, when you expand a binomial to the nth power, what it is we're starting with all of the power being on this first term here, this A-like term, and it's a trade-off of power as we go from the left to the right. Okay. So now the only other pattern that actually I want to share with everybody is this. When we took A plus B to the first power, we got 1 A to the first and 1 B to the first. But when I took A plus B to the second power, I got 1 A to the second, 2 A to the first, B to the first, 1 here. So I got 1, 2, 1. And when we look at the coefficients here, we say I got coefficients on all of my terms of 1, 3, 3, 1. This can actually be extended into what we call the binomial theorem. And we say it generalizes binomial expansions using combinations in something we call Pascal's triangle. So all of these coefficients that I'm referring to here are going to be derived from this Pascal's triangle. You notice that I'm using combinations in order to evaluate this here, but what I can tell you is just for right now, since this is an informal explanation of the binomial theorem, Pascal's triangle looks like this, but when you actually evaluate these combinations, you get this triangle over here on the right. We say it's 1, and then 1, 1, 1, 2, 1, 1, 3, 3, 1. Now wait a minute, I recognize these things. This 1 right here corresponded to A plus B to the 0. This 1, 1 here corresponded to my coefficients on A plus B to the first 1 and 1. This 1, 2, 1 corresponds to our A plus B to the second power. I got 1 of these, 2 of these, and 1 of these. And then so on and so forth. This A plus B to the third, we got 1, 3, 3, and 1 for our coefficients. So when we talk about Pascal's triangle, I'm going to share some information with you here. But we're going to refer to this triangle as having rows in it. So I would split it up, say, this way. And what I'm going to tell everybody is this is really important. We're going to say n equals 0 here, n equals 1 here, n equals 2 is this row right here, n equals 3, and so on and so forth, where n, we're going to say, is the power that we're raising our binomial to. Also this, Pascal's triangle, what it does is it gives coefficients in the expansion. Okay. So this is a really convenient thing to know, this triangle. As a matter of fact, I would say that you should memorize it, but in terms of memorize it, you don't really need to memorize it. You just need to memorize the patterns that are in it. Okay, so you'll notice that I've given a 4th row and a 5th row here. The important thing to recognize is that the first row is actually technically considered to be the 0th row. But these are going to give us our coefficients and our expansion. So when I say memorize it, but not really memorize it, know how to get it, what I'm really referring to is this. And we'll switch over to a different color here, how about a darker green. How am I getting these values? Well, Pascal's triangle, see, always starts with 1 and has 1s on the outside of it here. But you'll notice that when I say 1 here and then I get a 1 and a 1 here, how am I getting my 1, 2, 1 from my 1 and my 1 above? What we're really doing is this. We're saying if I were to add these two numbers, this 1 and this 1, I get this 2 right here. Okay, with 1s on the outside. Our next row here, we would say this. To get the 3's in the middle, we say add this 1 plus this 2, I get this 3. Add this 2 plus this 1, I get this 3, and there are 1s on the outside. Again, if you look at the next row, we say 1 and 3 spill down into a 4. 3 and 3 spill down into a 6. 3 and 1 spill down into a 4, and we have 1s on the outside. So this triangle, essentially, we could keep it going. We could say there's a 1 out here and a 1 out here, and my next value here would be a 6 because 1 plus 5 is 6. And my next value here would be a 15. Because 5 plus 10 is 15, and a 20 here, and we would say a 15 here, and a 6 here. So you'll notice that this Pascal's triangle thing is really easy to construct, and as a matter of fact, it's really useful in finding your coefficients. And last but not least, you'll see that there's a lot of patterns here, but the first one I want to, kind of admit that we have here is symmetry. It's kind of down the middle here. 1, 6, 15, 20, 1561, okay? So what I want to do is I want to use these patterns that we've kind of seen here to evaluate a plus b to the fourth and kind of generalize this. In the next video, we'll look at some more general, I don't want to say more general, but some specific examples of binomials that aren't just an a plus a b, but they have more substance to them, okay? So what I want to do here is I want to use Pascal's triangle and the patterns that we observed over here on the left in order to find a plus b to the fourth, but not have to actually take a plus b times itself 4 times. Nobody wants to have to do this. What we want to do is we want to say, well, look, I know that there are patterns that exist. So our first term here is like our a term. And our second term is like our, our b terms, our second term in the binomial. What we know is this: if I'm taking this to the fourth, the first thing we want to admit is this: n is equal to 4. The next thing I want to kind of do is this. I want to get myself set up with my powers. So essentially what we're going to do is we're going to say this. We're going to say, all right, well, it would be the first thing to the fourth power. The second thing, none of them existed at first. So for instance, over here, when we took a plus b to the third, we said the thing that came first in the binomial, which is our a term, was taken all to the third. We say there were no b's. We could say b to the 0 technically. So we say a to the fourth, b to the 0, but we're going to say that plus, now we're going to put in another set of parentheses where now the thing in the front loses a power, the thing in the back gains a power. So we say third first. When we expand this again, we're going to get squared squared. When we expand this again, we're going to say we're going to get first, third, and then last but not least, we're going to say over here, we get none of these and 4 of these. So the first pattern that we always observe is this: whatever the power is here, we're going to start with our first term getting all of that power and the second term getting none of it, and then it's going to just be a constant trade-off as we go from the left to the right. 3, 1, 2, 2, 1, 3, 0, 4. Once we have this, what we want to do is we want to fill in each of these blank sets of parentheses with the terms in our binomial. Now we notice that the first thing in our binomial is an a and the second thing is a b. So when we fill this in, what it looks like is this. We just say a, b, a, b, a, b, a, b, a, b. Now the last thing we need to do was just come up with the coefficients, and this is where Pascal's triangle comes in. How do I know what my coefficients should be here? One way to kind of tell you this would be this, essentially. You could go over here, you could say, all right, well, I need 1, 2, 3, 4, 5 coefficients. Shouldn't it be the row that has 5 terms in it? We say 1, 4, 6, 4, 1. Okay, so it's going to be 1, 4, 6, 4, 1. But the other thing I want everybody to notice is this. We were taking this to the fourth power. That's our n value. So we say the first row is actually the 0th row. So we say 0, 1, 2, 3. And we're going to go here where n would correspond to 4. And we say, okay, so my coefficients are 1, 4, 6, 4, and 1. Now, believe it or not, once you get the hang of this, this is way quicker than having to actually FOIL all these out and distribute and multiply all this stuff together and combine like terms and simplify. So speaking of simplify, the very last thing we usually do is simplify this expression right here. And the only thing I mean by that is essentially anything to the 0 power, let's recognize that that's just going to be a 1 anyways, and we can neglect it. And anytime we have a coefficient of 1, we don't really need to write that thing. So what we really truly get here in this final simplified form would be this. We would say, well, I had 1a to the 4th, so in other words, I have just a to the 4th, plus now I have 4a cubed b to the 1st. We usually would just write 4a cubed b. And then we say, okay, so we say plus 6a squared b squared, so a squared b squared, plus now 4a to the 1st, b to the 3rd, we could just write 4ab cubed. And then last but not least, we said plus 1 times b to the 4th, we could just say b to the 4th. And this would be our binomial expansion of a plus b to the 4th, okay? So in our next video, we're going to use these patterns again, but with a little bit more exotic terms. Cheers.